Okay, so we are going to talk about central force today. Central force এর আগে আমরা একটু নিউটনস ল অফ গ্র্যাভিটেশন দেখে নেব। নিউটনস ল অফ গ্র্যাভিটেশনের জন্য this is already done in your lower classes, so you don't need much of প্রি ইনফরমেশন অলরেডি জানা আছে, বাট সেন্ট্রাল ফোর্সের সাথে নিউটনস ল অফ গ্র্যাভিটেশনের খুব ইম্পর্টেন্ট কানেকশন। এর জন্য উই আর গোয়িং টু লুক ইনটু দ্যাট ফার্স্ট। Okay, so the main part of the topic is central force. So we are going to discuss about central force, and we are going to discuss about its property and all. But before we discuss about central force, one of the most common examples of the application of central force is Newton's law of gravitation. In fact, ইলেকট্রোম্যাগনেটিজমেও অনেক ল আছে যেগুলো আমরা পড়েছি। দ্য ইনভার্স স্কোয়ার ল, দ্যাট ইজ অলসো আ এক্সাম্পল অফ আ central force. So if we are talking about the Newton's law of gravitation, we know that we are having, let's say, two masses, okay, m1 and m2, and we know there will be a force of attraction between these two, and this force of attraction will be actually inversely proportional to the distance. So the three factors which are involved here are the mass, the distance between the two masses. So if I say this is my m2 and this is my m1, and let's say they are okay, so let's say the distance between these two masses is more or less r, and this will actually form an important part of the Newton's law of gravitation. So Newton's law of gravitation says that the force of attraction between these two masses is directly proportional to the product of the mass m1 and m2, and inversely proportional to the square of the distance between the two. Now we have to introduce a proportionality constant, and that is our universal gravitational constant. So this universal gravitational constant was calculated. There were a lot of experiments based on which this can be actually calculated. Cavendish experiment was one such experiment based on which we can actually find out what is the value of g. And using this experiment, the value of g was found out to be 6.67 into 10 to the power minus 11. Now if we talk about the unit, this is g, this side it is force, so I can cross multiply force into distance square. Force ka unit ho gaya, it's Newton, and distance is meter, it's square, so it's Newton meter square, and I have got two masses, so I can bring it at the bottom, so this would be the denominator, so this would be Newton meter square per kg square. So this is more or less my value of g. But this example that Newton's law we are talking about is actually nothing but an example of a central force. Okay, so central force we can actually define in a number of ways, but there are certain properties that will actually define it. Okay, so when we are talking about central force, certain things that we should remember is these points which are important. Okay, so if we talk about the central force, just a second. So when we are talking about central force, we are actually talking about r, which is the distance between the two bodies, right, from center to center. So that is from center to center. If we are considering central force, mostly we are talking mostly about point masses and so on. Okay, but if it's a larger body, we are basically considering it from the center to center. So between two bodies from center to center. Okay, so that's the first property or the first thing that we should actually note when we are talking about central force. And this force that we are actually having will always act along the line joining the two masses. So force acts along the line joining the center of the bodies, along the line joining the centers. Okay, so that's the one more point that we should actually know about central force. The third point which is important is, if someone tells you what is the property of central force, a central force is actually a conservative force. It's a conservative force. Now, if we are talking about a conservative force, there are a lot of definitions for that. The most important one is that in a conservative force, the work done only depends on the initial position and the final position, and it does not depend on the path. Okay, so that's very important. So we are going to look into more ideas of conservative force later. So if you're talking about central force, the Newton's law is actually one of the most important laws. Apart from that, we also have got the law between two charges. So if we are basically considering an example, Newton's law I've already told you. But if you're basically having two charges, there will also be a force acting between these two charges, and the force is nothing but the magnitude of the two charges. We can multiply that and divide it by the distance. That comes from our electromagnetism. And here also we have got a constant, which is k, which is 9 into 10 to the power 9 Newton meter square per Coulomb square. So this is the value that we have, and this k, if you remember, in class 12 also we usually do that, 1 by 4 pi epsilon naught. So this is also an example of central force. This is also an example of central force. So it's not that central force is not something which we have not studied before. We have already studied it once or twice. Okay. So now the important part is there are certain properties of central force. For example, I told you it's a conservative force. So we're just going to look into them point by point, and maybe we can see some of the proofs as well. Okay. So let's say I want to check the properties. Okay, so if you look into the properties, the first property is central force is conservative, and if you are considering the work done in a closed path, it is always 0. So the first one is, it's a conservative force, and it simply means that the work done in a closed path is 0. So that's the first thing that we should know about central force. The second property of central force is, the angular momentum. It talks about the angular momentum. So if you remember, angular momentum, it is more or less related with the rotational motion of the body. So if we can have a linear momentum, which is mass into velocity, the angular momentum would be nothing but moment of inertia into the angular velocity. Okay, so if you're talking about angular momentum, we usually denote it by L, and it's a vector quantity, and this can be written as m r cross v. So we can always take it in this form. Sorry. So just wait. So we can write it down as r cross v. So in general, what happens is, we know that L is equal to r cross p. Both obviously p and r are vectors, and p is nothing but mass into velocity. So I can write it down as r cross m into v bar. So if I do that, I can take out m and it will be r cross v. So here everything is vector. This is the position vector, directional vector, and obviously this is nothing but the velocity. And this angular momentum under central force of a body, this angular momentum of a body, that means the body is rotating, and we are talking about rotation, for example, the planetary motion and so on of a body, and central force, right? Under central force is conserved, always conserved. So that's how we think about it, but we do have a very small proof for that. We can also prove it. Now if you look into the proof, the first thing that we should note is that if someone says that dx divided by dt is equal to 0, this can only happen if this x is actually a constant. So this is the basic calculus knowledge that we should have. So in general, if we are talking about our Newton's second law, we know that force is equal to mass into acceleration. Okay, or in general, if you look into the Newton's second law, it says the rate of change of momentum is directly proportional to the impressed force. That means we can also say that force is equal to rate of change of momentum. That means dp divided by dt. And this actually gives me what is mass into acceleration, because momentum is mass into velocity. So I can take mass out, it will be nothing but dv divided by dt, and I can get mass into acceleration. So it is rate of change of momentum. So this is force. But if you are talking about a circular motion, force will be replaced by torque. So what we can do is we can write down what is our torque. So our torque, we usually denote it by tau, it's a vector quantity, is the rate of change of angular momentum. So rate of change of angular momentum. So that is important. So if you talk about angular momentum, you can write it like this. And this particular quantity, rate of change of angular momentum, will actually be 0. Okay, dl by dt is equal to 0. Now why this is the case? Because the torque is 0 in a central force problem. I'll tell you how. Let's say you have basically have the sun. Okay, you have the sun here, and the planet is revolving around it, and at any particular point, you can see what will be the force. Now this will always be directed towards the center. The force is directed towards the center, and at the same time the position vector will always be directed towards the center as well. The displacement is also away from the it's a distance towards the center. So that means the angle between f and r is 0. The angle between f and r is 0 degree. Okay, if you are talking about a central force, that means a rotational motion. Okay, it is moving like that. And what is the relation between torque and force? Torque tau is equal to nothing but r cross f. R cross f. So r cross f means it's rf sine of theta, and in theta in this particular case is nothing but 0 degree, and sine 0 is 0. So that means I can take it as 0. As a result, I can say that torque is equal to 0. But from calculus, we know that if the differentiation of a quantity is 0, that means that quantity is a constant, because differentiation of a constant quantity is 0, right? Hence, we can say, so it's a very small proof that L is a constant. So that is important when we are actually talking about the central force. Conservative force, angular momentum is always conserved, and this is important. We have also seen this before as well, but we have central force ke liye bhi we have to say that the force will more or less be conserved. Okay. So the next thing is we can talk about is the third property. And the third property actually talks about the potential energy. So the potential energy in a central force. So a body is rotating, it will have the kinetic as well as the potential energy. So the potential energy of a central force U, okay, we'll denote it by U, is equal to K divided by R. Okay, so what does it mean? That the potential energy, K is a constant, is inversely proportional to the distance. So you have to remember that the force is inversely proportional to square of the distance, but the potential energy is inversely proportional to only the distance. Okay, and this K is a constant. So this is important. We are going to just look into this. We can take any central force problem. We can talk about Newton's law, or we can talk about the force between two charges, and we can find it out as well. Okay, so in this case also we can try to prove it. Okay, we can try to prove it. So this force that we are talking about between two masses or two charges in, as a matter, is equal to nothing but force which is actually position of function of r, obviously it's a function of position, into whatever is the direction. So it's a vector quantity, so we have to represent it in terms of direction. Okay, now this force that I'm talking about here in this particular case, this f of r bar will be actually equal to nothing but g m1 m2 divided by r square. So this would be g m1 m2 divided by r square. Okay, so this would be a force, and we can actually use this relation. Now if you are considering a conservative force, just like conservative work done, we can actually find out the relation between force and potential energy. So if you're talking about a conservative force, so we can say for a conservative force, okay, F bar is equal to minus of del u by del r. Okay, this is the relation that we have. You might have seen this before also, and we can actually use it. So in general, if I want to find out the potential energy from this, what I can do is I can simply write it down as du. We know that the force is a pure function of only r, so I can take total derivative instead of partial derivative. I can take du on one side, and I can take minus f dr on one side if we do the cross multiplication, and we can integrate it on both sides to find out the total potential energy. So if I want to take this would be u is equal to minus, let me just take it out, integration. Now if you consider any force, it may be the gravitational force, or it may be the electrostatic force between two charges. Every time you have some parameters on top, and at the bottom it is r square, and the parameters on the top is more or less a constant. Okay, so let's mark this constant as k. Okay, it can be a gravitational force, or it might be a force between two masses. Every time the numerator is a constant, and we have got just the quantity which is at the denominator, so it is 1 divided by r square dr. So this is the potential, right? So if we just try to integrate this, we can simply write it down as minus, and let me just take this k outside, and this would be nothing but r of minus 2 plus 1 divided by minus 2 plus 1. So if we take it, we can take the constant c as well, but that's just a constant. So that would be a constant. So it is minus 2 plus 1 is minus 1. So minus minus will get cancelled, and I will simply get it to be k to the power. This is minus 2 plus 1 is minus 1. So it is k divided by r. So in this way, we can see that the potential energy that we are actually talking about is actually inversely proportional to r. So we can prove it that way also. But for that, we should know what is the relation between potential energy and force. So this is the relation that we are actually using. Okay. One more property which is there. Okay. Number 4. This is something which is again important. Since we are learning it in detail. So if we are basically considering for a body moving under central force, for a body moving under central force, what happens is that the angular momentum will actually move only in a particular plane. It's not going to going into the z plane if it is in the xy plane confinement. Okay, so its motion is confined to a singular plane. Its motion is confined in a single plane. So that means, if we're basically going to understand about plane, it means we're going to talk about the x, y, and z axis. So in general, if I'm talking about a planet revolving around the sun, and we know it does not revolve in circular orbit, it revolves around the elliptical orbit with the sun at one of its foci. That's the Kepler's law. We are going to look into that later. Here we know that the planet is revolving, and it will be revolving in such direction, okay, where you will be having the velocity at particular point will be actually nothing but tangential, okay, and the force will always be directed towards the center, and this is going to revolve in this. So that means this lies in the xy plane, okay. We know L is constant, so we know we can talk about this, and we know this is actually confined in a plane. So whenever we are talking about a central force, this will be more or less confined in a plane, okay. So that's important, okay. The next thing is Kepler's law. Okay. So Kepler's law is an important part when we're talking about planetary motion. What happened was initially it was Tycho Brahe. Okay, there was. Okay, can I take it in the previous page? No. Okay, we can write it here. So we can talk about Kepler's law. So Kepler's law, initially there was Tycho Brahe, who actually has gone through all the trouble of taking so much of reading by looking into the extraterrestrial bodies and planetary motion and so on, and all those datas that he collected, he actually could not explain it during his lifetime. What Kepler did was he actually took out all those datas and he analyzed them, and based on that he actually has given his law of planetary motion. So planetary motion is important. So if we are talking about the motion of the planet around the sun, what will be its position, how will you predict its time period, and all are more or less based on Kepler's law. So Kepler's law basically has got three laws, okay. Let's talk about the first law. So the first law says that all the planets that we usually have, all planets, it will actually revolve around the sun in elliptical orbit, okay, around the sun in elliptical orbit, okay, with sun at one of its foci, with sun at one of its foci. So your syllabus doesn't ask for the derivation part, so we are not going to derive it. We are just going to discuss the Kepler's law. So the Kepler's law might be you have to give all the three statements. That's important. Apart from that, you might need to explain it, so that's important. So as I said, that if we are talking about the planetary motion in general, what we have here is, let's say we have the sun, okay, and we have the sun at the center, okay, the sun at the center, and the planet will actually revolve around the sun. So if we have the sun at the center, the planet will revolve around it, but this planet that is actually revolving around the sun may not be following a circular path. In fact, it doesn't follow a circular path, it will follow an elliptical path. So the shape of an egg, it's an ellipse, okay, it's an elliptical path. And in an elliptical path, we know there are two focus, okay. If we are talking about an ellipse, in general, if I draw an ellipse and I can draw the axis here, maybe this is one axis and this is the other axis. The smaller axis that we have, okay, is denoted by, let's say, B, okay, and this is called the minor axis, okay. This is the minor axis, the smaller one, okay. The larger one is denoted by A, okay, and this is the major axis. So if you are taking only half of it, it is the semi-major axis, and if you are talking about the full axis, that's the major axis. So this is the major axis, this is the minor axis, and the focus will be lying anywhere on the major axis. So this will be one focus, this will be the other focus. So if we are talking about a planet somewhere here, okay, any of the planets, okay, the sun will be any of these foci, it will be either here or here. So that's how the statement goes. All planets will revolve around the sun in elliptical orbit with the sun at one of its focus. Okay, so this will be revolving around this. So I can say the planet is here. That means with respect to the planet, if it is following an elliptical path, the sun will be at one of the focus. It might be having two focuses and it will be here. Okay, so foci, we have got this result. So this is my first law is actually talking about the area swiping. Okay, so second law ये बोल रहा है कि position vector of the planet from the sun. So if you are basically joining the position of the planet with the sun, and we are trying to move the planet from one point to another in a definite interval of time, it's going to sweep equal areas. Okay, so line joining the sun and planet, so what happens is it will sweep equal areas in equal interval of time, equal areas in equal interval of time. So that's actually the idea behind the second law. What it means is that if I have a planet, okay, and we are measuring the time at different points. So let's say this is my orbit and this is the place where the sun is, and I am joining a line here. The planet is somewhere here, and let's say after some time the planet reaches here. So these are the two positions of the same planet, and the time in which it reaches from this point to this point is delta t. So it has covered some area. If you look into this joining the line, we can see that if you're joining the line, this has covered this much of area. Now at any other instant, if we are talking about the planet, suppose it has reached at this particular point, but here also the time that it takes from coming from here to here is delta t. The time is more or less the same. So if that happens, then also this area will remain the same. So if we consider this sun, whether this part or that part, nearer or closer, in equal interval of time, it will actually cover equal area. And this is the Kepler's second law. So that is again important. So explanation is important. Apart from that, what exactly the law states. The third law, if you are talking about, okay, the Kepler's third law is actually called the law of periods. Okay, Kepler's third law, and this is actually called the law of periods. So it talks about the time period here, and this talks about the semi-major axis as well. Okay, so it states that the square of the time period of a planet around the sun is directly proportional, your syllabus has got statement for this, so you should read the statement and kind of remember this. This is not something which is you have to write it exactly, but more or less if you try to reframe also, it's not going to change much, so you have to more or less remember this. The sun is directly time period of the planet directly proportional to the cube of the semi-major axis. Okay, semi-major axis of the elliptical orbit. So this is my third law. So it simply says that if you actually want to measure the time period, and if you are actually measuring the time period, let's say in t, so this t square is directly proportional to the cube of the semi-major axis. So I said a major axis we can represent it by a, so this is t square is proportional to a cubed. Okay, so this is the idea of Kepler's third law. So these are the points which are important. Okay, in Kepler's law. So central force, Kepler's law, these are all more or less connected. Okay, so that's it. Okay, now what we can do is we can the next part we can actually talk about satellites. Okay, so satellites, it's a very important thing. What happened is that initially when we talk about satellite, it was the Doordarshan and all that we used to watch, okay, on television. That was actually all possible because of satellite at that time, which India launched. That's INSAT, the INSAT series. Okay, there are a lot of satellites under the name INSAT. Okay, we have such satellites which is actually telecasting these signals. So satellites are important in today's age because if you're talking about satellites, it can be more or less artificial or natural. So if you're talking about the planet Earth, if something is revolving around it, it's more or less a satellite. And if you're talking about an artificial satellite, we can talk about the INSAT series. Okay, man-made satellite. So artificial is man-made, and an example might be the INSAT series or whatever satellites that are being launched nowadays. On a private level also the satellites are being launched for internet services, and all also you are having satellites and so on. Okay, television signal, radio signals, mobile signals, all are made possible because of satellite. If you are talking about the natural satellite, that means an object which will revolve around the earth, and the best example is moon. So earth has got only one natural satellite, that is the moon. So if you go to any other planet, you will get other satellites as well. Okay, and you can say that these will actually revolve around the planet under the influence of gravity. Okay, revolves under the influence of gravity. Revolves under gravity. So if it is revolving and not moving away, it simply means that there are two forces which are actually acting on it, and both of them are balancing each other, and then only we can say the revolution is more or less there. So if you are talking about so let's say this is the earth. Okay, and let's say the radius of the earth is capital R, and we have a satellite which is actually revolving around this. We have got a satellite revolving around this at certain height. Whenever I say Newton's law of gravitation, it depends on the height as well. How far is it from the center of the earth? Okay, so if it is closer to the center of the earth, the force is obviously more. Okay, so if we are talking about this, and this is the radius of the earth, and let's say the height at which the satellite is revolving from the earth, let's say this is h, and the distance from the center of the earth to that particular satellite is nothing but small r. Okay, so these are some parameters that we have to remember in order to find out this relation, where m, some of the factors that we'll actually need will be this mass of the earth. So whenever you are deriving this relation, you have to remember this. So you can write m to the base e, mass of the earth, and small m, let's say this is the mass of satellite. Okay, this small m is mass of satellite. Capital R, let's take it to be the radius of the earth, of earth. And what else we need? We need small r, which is equally radius of the circular orbit. Okay, radius of orbit. Okay, apart from that we have got h, the height of the satellite. So height means from the surface. Okay, height of satellite. So these are the things that we should know. But in general, we know if something is revolving, that means there are two forces. If one of the forces is more, that thing will fly away. For example, you take a stone, tie it with a thread and try to rotate it with your finger, it will keep on rotating because there are two forces acting on it. At some point the stone might fly away because one of the force will be more, okay, or the string's tension will be more, so that the string will break and so on. Okay, so this depends on what kind of forces will be there. So if if you are basically considering a satellite revolving, that means we are talking about a stable orbit here. For a stable orbit, there should be two forces that should be equal and opposite, and these two forces are the centripetal force, and this centripetal force is actually balanced by the gravitational force. So if you're talking about the centripetal force, we have already seen it before also. You might have derived it before also. mv square by r. V square by r is the centripetal acceleration. Multiply it with mass, you will get the centripetal force is equal to the gravitational force. So our case, capital M is the mass of the Earth and small m is the mass of the satellite. So it is gmm divided by r square. Okay, we can simplify this square and this will actually get cancelled. Mass of the satellite doesn't differentiate or doesn't hamper the velocity. So if I want to find out what is the velocity of this particular satellite, I can simply write down this relation as v is equal to root over gm divided by r. So this would be the velocity with which the satellite will actually revolve. Okay, or if we want to write it down in more detail, we can simply write it down as v is equal to root over gm, and our small r is the total distance, so it will be capital R plus h. So you might have some numerical question जहाँ पे बोला गया कि what is the radius of the earth is given, or the height of the satellite is given, and based on these information you can find out what is the velocity of the satellite. So this relation will help me to find out what is the velocity of the satellite. We can also modify it further. If we say that the satellite is on the surface of the earth, okay, if let's say satellite is on Earth's surface, okay, Earth's surface, then what happens is that this force that is acting on it is nothing but m into g, right? Mass into acceleration due to gravity is equal to, again we can take this relation of gmm by r square. Okay, so if you are taking an object and if you are placing it on the surface of the earth, there would be a force acting downwards which is nothing but mg. Okay, and this will be actually given by this equivalent relation, and based on this we can we are planning to modify this. Okay, so here also I can cancel this m and this m. I can simply write down this g r square is equal to gm. So I can modify my relation further. I can simply write down v is equal to root over gm ki jagah we can write down g r square divided by r plus h. Okay, now here it is on the surface of the earth, so there is slight correction here. If it is on the surface of the earth, we know that it's going to be the radius of the earth and not small r. So since I'm writing this down as capital R, so let me not change the notation, otherwise it will be confusing. So this is capital R, ye bhi mera capital R, or ye bhi mera capital R. Okay, so this is r plus h. Now this small r that we are talking about is nothing, height is not there because we are saying it's on the surface of the earth, so this height will become 0. So that means I can simply write down this velocity as, okay, in this particular case there is no height, but in this particular case we have got r plus h. But the radius of the earth is very large. If we talk about the radius of the earth, it is 6400 kilometer. Okay, and let's say it is orbiting very close to the earth, so I can say h is very small, so we can modify this equation further. R square will come out of the root. I can write it down as r root over, then there is g divided by r, capital R. Okay, so we can write it down in this form as well. So this way we can write down our expression. If we now again simplify this, this is r to the power 1, this is r to the power half, so it will be root over of r. So I'll simplify this further. I can simply get it as g into r. So it's a simplification where we say that the planet is revolving very close to the surface of the earth, and this will actually give me what will be the orbital velocity. So if you're basically aiming to find out what is the orbital velocity, we can put the value. Okay, this is my orbital velocity. Please remember this, orbital velocity. This orbital velocity that we have is nothing but root over of g. So g is 9.8 meter per second square into r. So r, as I said, it is 6400 kilometer. So if I convert it into meter, it will be 6400 into 10 to the power 3 meters. So that means this is going to give me the result. If you do the approximate calculation, it would be 8 kilometer per second. This is the orbital speed of any satellite which is there, but the condition is it is near Earth's surface, near Earth surface. So so this is near the Earth. It is inversely proportional to r plus h. So if h is there and the height keeps on increasing, the velocity will actually reduce. That we can also see. But near the Earth's surface, the velocity will be approximately equal to 9.8 kilometer per second. The next factor that we should know is the time period. Now, if we are talking about this satellite revolving around the planet Earth, we know that it is actually revolving in almost a circular orbit. Okay, let's assume this to be a circular orbit. Now if you want to find out the time period, okay, velocity is distance by time, so time is equal to distance divided by velocity. So that means the distance is nothing but the circular path that is following. So that means we are talking about the circumference here. Okay, circumference divided by the velocity. So velocity in our case, since it's rotating and we have given it a name as orbital velocity, the velocity with which it orbits, so orbital velocity. Now it's a circular orbit we are assuming, and the circumference for a circular orbit is 2 pi r. So I'll write it down it as 2 pi small r, and small r means whatever is the distance of the satellite from the center. So let me write it down as small r plus h divided by the orbital velocity we just calculated, v naught, let's say. So I can write it down as 2 pi. You can write it down in different forms. It depends if there is a numerical question, whatever form you want to use, you can use and find out the answer. Okay, depends what are the parameters that are being given to you. So if you talk about this, we can use this relation is by r plus h hai, so I can easily use it. So this will give me root over of gm divided by r plus h. So we can simplify this. I can write down this as 2 pi, एक रूट ले लेते हैं बड़ा सा, and this r plus h अगर रूट के अंदर ले लिया, I can write it down as r plus h square divided by this is gm divided by r plus h. So this will become cubed, right? So this will be in terms of gm, it will be 2 pi root over r plus h cubed divided by gm. Okay, so this is my velocity. I can also write it down. Gm I know is equal to gr square. We have already seen it. Okay, in this particular case gm is equal to gr square, so we can replace that as well. So that will also give me another form of the relation, root over of r plus h cubed divided by g r square. Okay, so that is also possible. Here also again, if the height is very low, when we say when h is very small compared to r, then we can ignore this. So therefore we can actually have the time period as 2 pi root over r cubed divided by gr square. gr square. So this will become a bit more simplified here. I'll basically have it as 2 pi root over of g by r, or sorry, r by g. Now if I do that, I can put the value of g, r and pi and simplify this, and you will see that the time period that you get will be approximately equal to 1.4 hour. So that means it will take 1.4 hour to rotate the entire earth. Okay, if it is very close, the velocity is 8 km per second, so you can think about it in that way as well. Okay, and based on that we can actually find out the time period. So the question, sometimes they do ask you tricky questions and so on. Okay, so this is important. So that's it. Okay, I can